In our next section, we'll take a look at the 4 VHDL design units. The 4 VHDL design units are the entity, the architecture, the configuration, and the package. The entity is basically used to describe what the outside world sees, or it's analogous to the symbol. The architecture is used to describe the guts or the function of the model, so it would be analogous to the schematic. If you were to look at a schematic and you saw a symbol, you would have no idea what logic was inside of that symbol. So again, the entity would be the symbol, what the outside world sees, and the architecture would be the actual functionality inside of it. The configuration is used to associate an entity and an architecture. The VHDL language allows multiple architectures to be associated to the same entity. If you have that, then you can use the configuration to pick a specific entity architecture pairing. And then packages allow you to store reusable code inside of reusable code and reference it throughout your design. You can kind of think of it as a toolbox or a library that you can use throughout the design. The entity declaration describes the name of your model. At the top here is the format for the entity declaration. You start with the keyword entity, followed by the name of your entity. The entity name can be any alphanumeric name that you want to assign to it. But again, this is going to be the name of your block. After that is the keyword is. After the first line, you have your generic declarations and your port declarations. Generic declarations are used to pass information into the model. We use generic declarations, for example, to make our models parameterizable. The port declarations define the inputs and the outputs to the model. After that, you end your entity declaration in one of two formats, with either end the entity name or end entity and then the entity name. There are essentially two versions of VHDL that we use, an 87 version and a 93 version. In the 87 version, we end the entity with end entity name. In the 93 version, we end it with end entity and then the entity name. Now, through the rest of the course of this material, we're going to be focusing, or all the examples are going to be using the 93 version, as that's typically what is seen most often. But just be aware that there is an 87 version available. The 87 version can be compiled by a 93 compiler, but the opposite is not true. Generics are the values that can be passed into an entity at compilation time. We use them to make our entities parameterizable when designing hierarchically. The generic declaration is contained inside of the entity declaration. After type entity, entity name is, I type the keyword generic. Then, within parentheses, I list the generics. The format for a generic declaration goes class, object name, type, and initial value. The class signifies what can be done to the generic. Generics are almost always constants, and the keyword constant is usually left out. The object name is the name of the generic that will be used within your model. The type is the data type, which specifies the values that your generic can hold. Finally, you can assign initial value, but of course that is optional. As you can see in this example, the generic declaration itself is considered a statement and ends with a semicolon. Within the parentheses, the generics are listed with semicolons separating each one. Since the semicolon is used to separate the list, there is no semicolon after the last generic, as you can see after the word up. Also notice you can declare multiple generics in one line if they are the same type and initial value by separating them by using commas. Thus, TPLH and TPLHL are both generics of type time initialized to 5 nanoseconds. And TPHZ and TPLZ are both generics of data type time initialized to 3 nanoseconds. The port declaration is used to declare the I/O to your entity and occurs within the entity declaration after the generic declaration. Similar to the generic declaration, the port declaration starts with the keyword port and then, within parentheses, lists all of the I/O. It ends with a semicolon. The structure for a port declaration goes class, object name, colon, mode, and then type. The class is most always signal, though it doesn't have to be, so you almost never see the word signal actually appear in a port declaration. The object name is the name of the I/O port. In this example, the object names are clock, clear, and queue. Since clock and clear are of the same type, they are declared together, separated by a comma. The mode is the direction of the port. In VHDL, the keywords for directions are in for input, out for output, in-out for bidirectional, and buffer for an output with internal feedback. Typically, input signals can only be read from and not written to. Outputs can only be written to, not read from. In-outs must be used as both inputs and outputs. With buffers, physically in the device you will have an output pin, but you will be allowed to read from it as well. Use care when using buffers, as there are restrictions on them when connecting them to other design blocks hierarchically. Personally, I stick with in, out, and in-out. And lastly, the type is a data type that defines the type or values that can be held by your I/O. Like the generic declaration, the semicolon is used as a separator, and the last port declared is not followed by a semicolon, as you can see after the word bit for the Q port. The architecture describes the internal logic to your model, analogous to the design schematic. While the outside world could see the entity name, the parameters being passed to it, and the port connections, it cannot see the actual guts to the block. We use the architecture to describe the functionality and possibly the timing of the model. Architectures must be associated with an entity, but an entity can have multiple architectures associated with it. This is done sometimes in simulation when a designer wants to use two different sets of test vectors to test the design. He or she may have two architectures and will select which one they want to run at compile time. Multiple architectures may also be used by designers when they have one architecture that contains a synthesizable model of the design and another architecture that contains a simulatable model. Depending on what action they're performing, be it synthesis or simulation, they will select the appropriate architecture. Within the architecture are implied and explicit processes that execute concurrently, and we'll talk more about those later. When coding your architecture, you can use behavioral style modeling or structural style modeling or a mixture of both. The architecture starts with the keyword architecture. Following that is the name of the architecture. You can use any alphanumeric name for your architecture. In fact, many designers, including myself, will simply reuse the same name for all of their architectures or most of their architectures. Since architectures are invisible to the outside world, reusing the same name is not an issue. If you have multiple architectures for the same entity, then the names must be unique. After the architecture name, you have the keyword of, and then the name of the entity that this architecture belongs to, followed by the keyword is. Then you have the architecture declaration section. Local identifiers that you use inside of the architecture that are not ports or generics must be declared in the architecture declaration section before they can be used in the design. In this example, we see that we have a constant, a signal, and an enumerated data type. All of these we'll talk about in more detail later. After the declaration section, you have the keyword begin, followed by the architecture body. The architecture body contains the executable lines of code within the design, made up of various types of processes. End your architecture with the line end architecture and then the architecture name. Notice the formatting of the architecture shown in this diagram as well. By using proper formatting like this, your architectures are much easier to read. As you can see, the architecture declaration section is indented, whereas the begin and the end architecture are in line with the keyword architecture. The third design unit, the configuration, is used to associate an entity to an architecture. Since entities can have more than one architecture associated with them, the configuration assigns a unique name to a single entity architecture pairing. Then, instead of having to choose a pair, you simply select the configuration name and the tool understands which entity architecture pair you are referring to. While they are supported in synthesis environments, they are used more so in simulation environments where, again, I may have multiple sets of test vectors applied to the same entity. The format for a configuration starts with the keyword configuration, then the configuration name, followed by of, and then the entity name, is for, the architecture name, and then end for. You end your configuration with the keywords end configuration and then the configuration name. As a note, in hierarchical design, you can also use configurations to associate lower level components in an entity architecture structure. So here's an example putting together everything we've done so far. I start with the entity declaration. Entity, the name of the entity, CMPL_SIG, is. Next is the port declaration. This entity has 3 input ports, A, B, and select, and 3 output ports, X, Y, and Z. And then I end the entity declaration. Next is the architecture. The architecture is named logic, and I associate it to the entity name is. I don't have any architecture declaration, so that means that all of the names within my architecture have already been declared in the entity. Then I have 3 signal assignments or processes within the architecture, and again we'll talk about these in more detail later. I end the architecture with the statement end architecture and then the name of the architecture logic. At the end I have my configuration. My configuration is associating my entity name, CMPL_SIG, with the architecture logic, and assigns a unique name, CMPL_SIG_CONF, to the entity architecture pairing. Now, if I didn't have that configuration line, all the tools would understand that this entity architecture were pairing and when they would treat them as such. But we're just showing in this example how the configuration is used with an entity architecture pairing, assigning a unique name to them.